So in last video we have finished the linear expansion. Today we'll take next one, areal expansion or superficial expansion. It means whenever we heat a body, whenever we provide heat energy to a body, then as I said, the size of the body increases. The increase in area of the body is called areal expansion. So it is found that whenever we provide heat energy to a body, increase in area, that is a increase in area, is directly proportional to initial area of the body. Say A naught is the initial area of the body, and same increase in area of the body, delta A, is also proportional to change in temperature. We can represent by small t or capital T, right? So it is found that whenever we heat a body, increase in area is directly proportional to initial area and directly proportional to change in area. Therefore, we can write increase in area is directly proportional to initial area and change in temperature. To remove this proportionality sign, we can write increase in area is equal to, we have to add a constant. To remove the proportionality sign, we are adding a constant into initial area into change in temperature. Today, this proportionality constant, C, is written as beta. Therefore, delta A means change in area is equal to beta. This beta is the proportionality constant into initial area into delta T. So this is the expression for change in area of a body on heating, right? Next, see here, suppose if A is the area of the body at temperature T and A naught is the area of the body when temperature is T naught. If temperature changes from T naught to T, then we can write change in area is A minus A naught, that equal to beta into A naught. Change in temperature is T minus T naught. If I send this side, minus A naught becomes plus A naught, and after simplification we can write A equal to A naught becomes common in bracket 1 plus beta into T minus T naught. So this is the area of the body at temperature T. Today, for our study, we have to remember these two formulas. One is change in area formula, and second, area of the body at temperature T. And second, Here remember I said beta is the proportionality constant, and this proportionality constant is called as coefficient of areal expansion, coefficient of areal expansion, or coefficient of superficial expansion. Okay, see, you have to remember these two formulas, and in this I think this formula is very much similar to our linear expansion. Only difference is in the linear expansion we had L. Instead of A we had L. Means in linear expansion L, and in areal expansion we are writing A. That is the difference. Okay. And based on this, see, a simple question arises in this areal expansion. That is, whenever we take a body having cavity, consider this is a body having cavity. So this is a solid portion of the body. Okay, and this is the cavity portion. So whenever we heat this body having cavity, what happens to the size of the cavity is a very common question in our topic. Okay, so for that, see, whenever we heat a body having cavity, then as we know the expansion takes place. So misconception in the students is, okay, in expansion means of course this side increases, this side also increases, this side increases, this side also increases. As a result, they may think that this portion becomes this much, and they may think that this portion also increases on this side. As a result, cavity decreases. But in reality what happens? Cavity also increases. How it increases? For that, I have a simple example. Imagine we have a body without cavity. We have a body without cavity. See, this is the body without cavity. I assume it's no cavity, just I assume this portion. I assume this is the imaginary portion, no cavity. It is the imaginary portion. Imaginary portion. So now whenever we heat, then what happens? You know, this complete size of the body increases. To increase this size, the cavity size of the imaginary portion, should also increase. It means the size of this imaginary portion should also increase while increasing the size of the body. Now think, if we take this imaginary portion out, if I take this imaginary portion out, when I heat this imaginary portion, you know, the size increases. So based on these two, I can say when cavity is present or cavity is absent, means whether body is having cavity or body do not having cavity, whenever we heat, then size of the portion increases. That is a very important point to be remembered for solving questions. Okay, similarly, now I can go for volume expansions. This volume expansion is also similar to our linear and aerial expansions. It is found that whenever we heat a body, increase in volume is directly proportional to initial volume and increase in the volume of the body is directly proportional to change in the temperature. So it is found that whenever we heat a body, then volume of the body increases. That is called volume expansion. It is found that increase in the volume is first directly proportional to initial volume and directly proportional to change in the temperature. And if I combine both, then increase in volume is directly proportional to V0 and delta T. This is called proportionality sign. And to remove the proportionality sign, we can put a constant. We can put a constant into V0 into delta T. And today, this proportionality constant, I can write it as gamma. So delta V is equal to gamma V0 into delta T. So this is the change in volume of a body. Okay, where gamma is called as proportionality constant, and today this proportionality constant is called as coefficient of volume expansion. Coefficient of volume expansion. I think there is no much difficulty to analyze here. If I bring this V0 this side, then delta V by V0 is equal to gamma into delta T. So you know that this is nothing but change in volume divided by original volume. Change divided by original is called as fractional change. Fractional change. So this is called as fractional change in volume. Fractional change in volume. Similarly, I can write, if I multiply this by 100, we can get percentage change in volume is equal to gamma into delta T. If I multiply by 100, we get percentage change in volume. It means whenever we heat a body, then percentage increase in the volume is given by gamma into delta T. So this is a body. Whenever we heat, the size of the body increases from all sides. Okay, then thereafter, once again, if V0 is the volume of the body at temperature T naught, and V is the volume of the body at temperature T. Then if temperature changes from T to T naught, then final volume can be written as this. You can simplify using the knowledge of linear and areal expansions. V naught in bracket 1 plus gamma into T minus T naught. So this is our expression for final volume of a body, or volume of a body at a temperature T. See, today you have to remember first expression, second and third expression, right? So this is our volume expansions. As you know, for your information, this linear expansion, areal expansion and volume expansions are similar to our change in resistance of a conductor with temperature. Okay, so if you compare this with resistance or taking knowledge of resistance, you can analyze this. Okay, so after this, a very next point is relation between coefficient of linear expansion, coefficient of volume expansion and coefficient of areal expansions. Okay, see here. First I'll try to write L is equal to L naught in bracket 1 plus alpha into delta T. It is for linear expansions. A is equal to A naught in bracket 1 plus beta into delta T for areal expansion. V is equal to V naught in bracket 1 plus gamma into delta T for volume expansions. So this much we have taken till now. Next is, see, suppose imagine I have taken a body, I have taken a square body. If I take the square, you know, A can be written as A naught. Okay, first I take reverse. Since we know that L is equal to L naught in bracket 1 plus alpha into delta T. Here I can take a square or a rectangle. There is no change at all. But anyway, today I want to arrive the final expression, not the derivation. Okay, so that's why I prefer a simple method. Okay, so for that I take a square body. If I take a square body, now square on both sides, square on both sides, square on both sides, it becomes L square is equal to L naught square in bracket 1 plus alpha delta T whole square. See, this for square, okay, I'll write one more step extra. L square is equal to L naught square in bracket, it is like A plus B whole square. Then it becomes 1 square plus alpha square into delta T square plus 2 into 1 into alpha into delta T. So 2 alpha delta T. Since alpha is very small, Hence, alpha square can be neglected since alpha is small. Therefore, alpha square is neglected. Alpha square is neglected. If we neglect the alpha, then means if alpha is small, then alpha square is further small. Alpha square is very small. Very small. Hence alpha square into delta t square can be neglected. Means this term is neglected. When I neglect this term, then remember this L square, if I take a square body, L square is nothing but A square. L naught square is nothing but A naught in bracket 1 plus, if I neglect this become 2 alpha into delta t. So this is our arrived expression, okay? When I compare this equation with this, then we can say everything A naught in bracket 1 plus here delta t, here also delta t. Means instead of beta, here we have 2 alpha. Hence I can say beta is equal to 2 times of alpha. Here this I can arrive in one step also. That is, see, if I assume this is very small, according to binomial expansion, you know, this power should be multiplied to the second term. That is 2 alpha delta t. 2 alpha delta t, that is the same. Okay, now next. For volume expansions, we know L is equal to L naught in bracket 1 plus alpha into delta t. Now instead of square, now cube on both sides. Cube on both sides. It becomes L cube is equal to L naught cube in bracket 1 plus alpha into delta t cube. If I expand binomially, it becomes L cube is equal to L naught cube in bracket 1 plus, this power is multiplied to second term, that is 3 alpha into delta t. You know, L cube is nothing but what? Volume V. This becomes V naught in bracket 1 plus 3 alpha into delta t. Right? So based on this, I can say, if I compare this with this equation, V equal to V naught in bracket 1 plus gamma into delta t, here 3 alpha into delta t. It means 3 alpha is the same as gamma. That is, gamma is equal to 3 alpha. So pause the screen, if you want you can note down. Next, see, based on these derivations, our final conclusions are beta is equal to 2 alpha, gamma is equal to 3 alpha. It means if I ask you, the ratio of alpha is to beta is to gamma. Then I can write this alpha as it is. This beta can be written as 2 times of alpha. This gamma can be written as 3 times of alpha. Since alpha is common, so alpha is to beta is to gamma is equal to 1 is to 2 is to 3. This you have to remember, okay? Or otherwise, we can write in terms of alpha also. Okay, this is the relation. That is, alpha is equal to beta by 2 and gamma by 3. That we can arrive here, because here alpha is equal to, if I bring it this side, it becomes beta by 2. Here if I bring 3 this side, it becomes gamma by 3. So this is the relation. Now I should go for percentage change in area. Percentage change in area. That I have to prove. These 2 points are proved now. Now the next points. See, as you know, delta L is equal to L naught alpha into delta T. If I bring it this side, delta L by L naught is equal to alpha into delta T. This is called fractional change in length of the body on heating. This is called fractional change in length. Similarly, if I multiplied by 100, we can get percentage change in length. Delta L percent is equal to alpha into delta T multiplied by 100 will give you percentage change in length of the body on heating. Next, see, whenever I take area, delta A is equal to A naught beta into delta T. Okay, if I bring A naught this side, then delta A by A naught is equal to beta into delta T. You know, this is called fractional change in area. Fractional change in area. So, see, if I multiplied by 100, we can get percentage change in area. That is equal to, instead of beta, I can write 2 alpha, just now we proved, into delta T multiplied by 100. So, when you look at this alpha delta T into 100 is nothing but percentage change in length. Therefore, percentage change in area is equal to 2 into percentage change in length of the body. So this what is our next point. Similarly, next we go for volume. I think based on this now you can analyze. You know, delta V is equal to V naught gamma into delta T. If I bring this V naught, then it is delta V by V naught is equal to gamma into delta T. You know, it is called fractional change in volume. if I multiply this by 100, we can get percentage change in volume is equal to gamma into delta T into 100. Will give you percentage change in volume. Now I can substitute, see, percentage change in volume is equal to this gamma can be written as 3 into alpha into delta T multiplied by 100%. Now you can compare. See, you know, alpha into delta T into 100 is nothing but percentage change in length. Therefore, percentage change in volume is equal to 3 times of percentage change in length, delta L%. Okay. So this is our relation, that is percentage change in volume is equal to 3 into percentage change in length. Okay, please pause the screen and copy. After this, next point is the 3 coefficient of expansions are not constant for a given solid. Their values depends on temperature range in which they are measured. In thermal properties of matter, in NCERT book you get a graph of variation of coefficient of copper with a temperature. Okay, hence in one word remember it is not constant. This alpha, beta and gamma changes with temperature. Means not for small change in temperature, they changes when there is a large change in the temperature. Okay, so remember one more thing, the value of alpha, beta, gamma are independent of units of length, area and volume. Whether you take the length in terms of meter or you take in terms of centimeter or you take in terms of millimeter, value of gamma remains same. Okay, so this you have to remember. Pause the screen and note down these important points. Okay, it's also very much important. So far what I said, whenever we heat a body, because of vibration of the atoms or molecules, size of the body increases. But there are some materials like rubber. Whenever we heat, they get contract. Why they contract means because transverse vibration of atoms of the substance dominate over longitudinal vibration. Because of this, instead of expansion, they contract. It means one, remember, on heating, most of the substance will increase in the size. The size of the most of the atoms increases. But there are some materials, their size decreases on heating. Okay. It's one of the most important word is and important point is error in scale reading due to expansion or contraction. So this is somewhat confusions to the students also. To avoid the confusion, I'll take little bit slow. Okay. See, at a normal temperature, say theta, here I am representing the temperature by theta. Say it is my scale. It is the scale. And 3 cases I will take. So in first case I will take the size of the scale is this much. In second case I will take size this much. In third case I will take the size of the scale less. Okay, right, fine. See, I'm representing this as value. There I have taken A, B something. Okay, say it is A. Or otherwise I take one more thing. This is the value A. Here, okay, I'll represent that later. Suppose imagine this is our body whose length is to be calculated. It is a body whose length is to be calculated. It is the scale which is used to measure. It is the scale which is used to measure. Say when temperature is theta. Now the size of the body is called true value. True value. Size of the body is called true value, and whatever measurement we make is called scale reading. Scale reading means measurement taken from the scale is called scale reading, right? See, I am heating the scale, not the body. Hence, size of the body remains same. Size of the body remains same. So this is the first case. This is the second case. This is the third case. In all three cases, size of the body remains same. Means whenever we measure using the scale, whenever I measure using the scale, I will take the scale size little bit more. Say, I should get the value A only. Whether temperature here more than theta, here theta dash is greater than theta. Here I am measuring the length at a temperature which is less than theta. At all temperatures, I should get the length as A only. But what happens whenever I heat the scale which is made up of metal, the length of the scale increases. As length of the scale increases means here first will be as it is. Actually, because of increase in the length, the position of A also goes here. This is the position of A. Position of A. Right? So now what happens? Say it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 something. Here also 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 something here. Means the length should increase now. So here it is a 10. Now actually here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So length is equal to 10 here. Now if I divide exactly into 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now length becomes 8 only. Because of increase in the size. Here if I analyze, here I am taking true value is equal to scale reading. Here you know this is a true value. Length of this is called as a true value. True value. This is called as a scale reading. But here if I look at, it seems that scale reading increases. But you know already 10 means, instead of this I'll write here, this is a scale reading is 8. Scale reading is 8 now. But true value here also, true value is 10. Here also true value is 10. Right? So if I take in this case, now whenever the temperature is decreased, the length of the scale decreases. Now the position of A becomes here only. It means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now scale reading is 12, but true value remains 10. Based on this, I can say a true value is equal to scale reading. Here we know that true value is greater than scale reading. Here true value is less than scale reading. Now question, how much scale reading is more? How much scale reading, true value is more than scale reading means this difference is because of expansion. Difference is because of expansion. Hence I can say true value is equal to scale reading plus increase in the length. Increase in the length. So true value is equal to scale reading. Today scale reading is taken as initial value plus, because scale reading is taken as initial value now. So according to increase in the length is equal to initial length alpha into delta t. Today initial length is nothing but scale reading into alpha into delta t. Therefore true value can be written as scale reading is taken common 1 plus alpha into delta L. Sorry, not delta, it's delta t. This is the case when temperature is increased. In this case, scale reading is more, true value is less. Then this is subtracted. Instead of addition, here it is subtracted. Okay, so that you can look at here. Same I have arrived here. Right now you pause the screen and note down this much. And tomorrow I will start questions based on linear expansion as well as areal and volume expansions. We'll start questions in the next video.